Okay, so the next speaker is Zhang, who will talk about the classical zero-knowledge arguments for quantum computations.
Thanks. So it's going to look like I copied Robin, but I didn't. We just have the same idea, which is to go through the title and explain the phrases in it, which I think will clarify the purpose of the result. So the first term I want to clarify is the word arguments. What do I mean by an argument for a quantum computation? And to do that, I need to go over interactive proof systems, which Robin already mentioned briefly. So an interactive proof system is a protocol involving a verifier who is efficient and a prover who is unbounded. And the prover attempts to convince the verifier that some problem instance X is in some language L. And in order to be called a proof system, the protocol should be complete and sound. So I've written the definitions of completeness and soundness up there. So for completeness simply means that for any X in the language, for any yes instance, there is an interactive proof, which the prover can offer the verifier that causes it to accept. Soundness means that for any X not in the language, there's nothing the prover can do which will cause the verifier to accept, except with some probability, some small probability Q, which we can decide. So we can define complexity classes using interactive proofs, and I'll just remind everyone what QMA is, because it's important to the talk. So one example of a class defined using an interactive proof system is QMA. And QMA is defined as a class of languages which have an interactive proof system involving a quantum polynomial time verifier and an unbounded prover, such that, so when X is in the language, the verifier will accept with probability at least 2/3. When X is not in the language, the verifier accepts with probability at most 1/3. And the number of messages that the prover is allowed to send the verifier in this protocol is 1. So the message can be quantum, but the prover is only allowed to send one message, and this message is usually referred to as a witness. So an interactive argument system is exactly the same idea, but the protocol needs only be sound against efficient provers instead of unbounded ones, and for our purposes, efficient will mean quantum polynomial time. Okay, so the second thing, which I want to clarify briefly and remind everyone after the last talk, is zero knowledge. So a zero-knowledge proof system is a proof system in which if the input is in the language, then the verified learns nothing except that the input is in the language. So this is usually shown by constructing a simulator. So the simulator knows, this is very vague here, but the simulator knows only what the verifier knows. And so the simulator takes in X and outputs transcripts that when X is in the language are indistinguishable from real transcripts. So if the indistinguishability is computational, then we call it computational zero-knowledge. If the indistinguishability is statistical, as in the distribution is close, statistically speaking, between the real transcripts and the simulated transcripts, then we call it statistical zero-knowledge. And I'll primarily be talking about computational zero-knowledge here. So basically, this means intuitively that whatever the verifier learns from interacting with the prover in a real instance, it could equally have generated it itself if X is in the language. So it basically doesn't learn anything from the interaction. The last part is what do I mean by arguments for quantum computations? And I think this will be clarified when I talk shortly about an ingredient that we used in order to produce this result. So I will skip past it for now. So now I'm going to go through two different protocols that we put together in order to get our result. And the first one is a classical argument system for quantum computation. So what does that mean? I'm referring to the celebrated result by Mahadev in 2018, which is a classical verifier argument system for QMA. So for QMA means that we can decide any problem in QMA using this argument system. And it's an argument system. It's sound only against quantum polynomial time provers. Now, why do we care about this? There's a problem called quantum verification. And it basically asks, is BQP in IP BQP? So IP BQP we can define as a class of languages for which there is an interactive proof involving a classical verifier and a quantum prover, unbounded quantum prover, such that the honest prover is efficient, but the protocol is sound against unbounded provers. And so Mahadev did not, well, firstly, why do we care about this problem? We can imagine that in some years when we have large-scale quantum computers, we want to know if they can really decide problems in BQP using only classical machines to test them. Now, of course, some problems in BQP are in MP, and by definition, MP is the class of languages that can be efficiently checked, so this is okay. But what if there are problems in BQP that aren't in MP? How do we verify that these are actually solved by our quantum computers? And the answer is that we can ask the quantum computer to offer a proof to us, basically, an interactive proof that they solved the problem correctly. So this is why we care about IP-BQP. Now, Mahadev's result doesn't quite show this. It shows that QMA is in QP-IP0, where QP-IP0 is simply the same class as IP-BQP, except that it's not a proof system anymore, it's an argument system. So it only has to be sound against quantum polynomial time provers. And for this result to hold, you have to assume that the efficient prover is provided access to the quantum witness in the QMA instance. So, of course, there might be problems in QMA that aren't in BQP, so it's not necessarily clear that the prover, if he is efficient, can come up with the witness on his own, but if you assume that he's given the witness, then this result holds. So the second ingredient that I want to cover, which we put together, is a zero-knowledge, computational zero-knowledge interactive proof system for QMA, and this was by Broadbent, Zhang, and Watrous in 2016. And this protocol is between a quantum verifier, who is efficient, and an unbounded quantum prover. And basically what we do, we put together the zero-knowledge interactive proof system for QMA and the classical verifier interactive argument system for QMA, and we get a classical verifier zero-knowledge argument system for QMA. So how do we do this? So Mahadev's key contribution to the problem of quantum verification was a measurement protocol. And intuitively, the measurement protocol allows a classical verifier to force an untrusted but efficient prover to produce honest measurements of its quantum state. I won't go into the details here, but this is the result. And in the Broadbent protocol, which is an interactive proof system for QMA, the only quantum thing that the quantum verifier needs to do is measure. Everything else in the protocol for the verifier is classical. So combining these two protocols is quite a natural thing to do. Of course, it's not entirely trivial. We had to make a few changes in order to make it work, and I will go through those as I proceed through the protocol. So I'm now going to show a brief outline of the protocol, and hopefully it will clarify what we've done. So firstly, I need to talk about the inputs. So there's a problem called the two local xz Hamiltonian problem. And basically, the input to this problem is a Hamiltonian h and two real numbers a and b, which define a promise about the lowest eigenvalue of h. And the problem is to decide if the lowest eigenvalue of h is less than a or greater than b. You'll promise that it's one of these two. It can't be in between. And this problem turns out to be complete for QMA. So you can reduce any problem in QMA to this, or alternatively, if you can design a protocol that allows you to decide problems of this kind, you can decide any problem in QMA. So we're going to rely on this problem. And here's a diagram of the protocol. So as you can see, HAB is input to both prover and verifier, or it's stuck in the sky so everyone can see it. And so let's talk firstly about P1. So P1 takes as input the quantum witness for the QMA instance, rho, and it implies an encryption keyed by K to rho. And furthermore, it sends a commitment to K to V2, the verifier. Now, if you're not familiar, I assume many of you are familiar with commitments, but if you're not familiar, you can think of it as an encryption scheme such that each ciphertext corresponds to only one key and message and randomness. So basically, when you have sent the commitment, it hides the message that you sent, but if someone else comes along later and asks you to reveal your randomness and key and reveal the message, you're locked in. You can't change your mind about what message you sent. You can't deny what message you sent, basically. So this is what P1 does. It encrypts the witness row and passes it along, and also sends this commitment to the key. Now, the encryption scheme is not a real encryption scheme. It doesn't satisfy CPA security, for example, but you can think of it for the purposes of the scheme as one, in that it hides the witness and also prevents tampering. And why this is important will come up shortly. So now let's talk about the next stage, which is a coin flipping protocol. So in order to decide whether the lowest eigenvalue of the Hamiltonian is less than A or greater than B, intuitively what we want to do is, intuitively many protocols work like this. The verifier decides randomly to check a particular term of the Hamiltonian. It measures this term against the witness, and if it obtains a small measurement result, it accepts, otherwise it rejects. So intuitively, the sum, if the lowest eigenvalue of h is small and you measure just one term, then you should expect to get something small if you measured it on the witness. So the coin flipping protocol is here to ensure that neither the verifier nor the prover can bias the outcome, bias the choice of the term that the verifier is going to check in its favor. So essentially, it's just a way that two parties can compute a trusted random string that neither of them can bias as long as one party is honest. So this produces a term hi, which the verifier is going to check by measuring. And that leads to the measurement protocol, which is the Mahadev measurement protocol. And I'm not going to go into details, as I said, but we can point out one important detail here, which is that how is a classical verifier able to constrain a quantum prover so that the quantum prover has to produce honest measurements of its quantum state? The quantum prover is more powerful, after all. And the answer is that you use some computational assumptions. So you have the verifier generate some trapdoor one-way functions along with the trapdoors to these functions, and then use those one-way functions in the protocol. And this allows the verifier to have some knowledge advantage over the prover, and so allows it to constrain the prover in some sense. So I put a little green tau there to remind us that the verifier has a secret state, the trapdoors. And so basically now the verifier measures the term hi that was selected in the previous stage. Now there might be a confusion here, which is that the prover has applied an encryption to rho. And basically it's supposed to execute the measurement protocol on the encrypted version of rho, not the actual witness, so that it remains zero knowledge. And the question is how can you be sure that it's encrypted? How can you be sure that measuring an encrypted version of the state will really tell you anything? And the answer is that this encryption happens to be to admit transversal applications of Clifford gates. So applying the measurement and then encrypting is the same as doing it the other way around. They commute. And so basically, it's OK to measure the encrypted state and then unencrypt if that's what you want to do. OK, so now let's move on to P4. So P4 is going to receive the measurement results that V3 got in the measurement protocol. So in the measurement protocol, P3 actually doesn't know what the results are that the V3 is getting. But V3, of course, knows. And now V3 is supposed to send these unaltered to P4. And P4 is going to check that they are indeed unaltered. Now, there's another question here, which is how could P4 possibly know if they are altered or not? The verifier could just XOR a random string on it, and how would they know? The answer is that the encryption scheme that we applied to rho in the first step, so that P1 applied, is also an authentication scheme. So the authentication properties should make sure that if V3 decided to tamper with the measurement results, then P4 should be able to detect it and subsequently reject V3. If it doesn't reject, it goes on to the last stage of the protocol, which is an MP zero-knowledge proof protocol. And it's known that any statement in MP can be proven in a zero-knowledge way. And now the key insight here is that you can phrase the So you don't want to actually give the commitment key, the key that we committed to, that P1 committed to the verifier, because this might not be zero knowledge. But you can prove that the following statement. So I'm the prover. Given the commitment that I sent earlier, there is only one key that I could possibly have committed to. I'm not going to tell you the key. But given this commitment and given all the rest of the transcript, basically, if you had that key, you would accept. Now this is an MP statement because you can check it easily with a witness. The witness is the key. So because this is an MP statement, we can prove it in a zero knowledge way. And this basically finishes up the protocol. Now the first change that we had to make in order to make this work is replacing the Clifford Hamiltonian problem with a two-local XZ Hamiltonian problem. And so Broadbent et al. Used another QMA complete problem called the Clifford Hamiltonian problem, in which all the terms are Cliffords. We replaced it with a Hamiltonian in which all the terms are poorly X's or poorly Z's, and this is just because it's not clear how to make Mahadev's measurement protocol work for measuring Cliffords. So this is something we had to do. The second thing we had to do is split the coin flipping protocol into two stages. So in the Broadbent et al. Protocol, what happens is that the prover P2 physically sends the witness to the verifier, or the encrypted witness rather, to the verifier. And so when the measurements take place, which the verifier does itself, the prover cannot possibly change its mind about the set state that it sent. But of course, in here we can't actually send the state to the verifier, so the prover holds onto it. And then what happens, of course, P3 could change its mind about its state after it finds out what HI is, if it found out what HI is. It's much easier to construct a state that only satisfies one term of a Hamiltonian versus all of the terms. So what we do instead, we simply have the verifier hide what HI is, but commit again to the value of HI basically, so that later it can reveal and show that it did not cheat in this process. But when the measurement protocol is taking place, P3 does not know what is the term that's being checked. And the last step that we had to do, which is maybe the most non-trivial, is add a trapdoor check. So I mentioned earlier that during the measurement protocol, the V3 holds these secret trapdoors tau. Now, the measurement protocol happens to require the prover of the protocol to perform some quantum actions that no classical machine should be able to efficiently simulate. But recall that for zero knowledge, we want to show that there is a simulator. And moreover, we want to show, because our verifier is classical, in order to intuitively satisfy the requirement that whatever the verifier learns, it could have generated itself, we want the simulator to be classical. Now, how is this possible if the protocol requires that the prover perform some quantum actions that no actual classical machine can simulate? And the answer is a classical machine could simulate these actions if it was given access to the trapdoors. And of course, you can't ask the verifier to reveal the trapdoors during the measurement protocol, otherwise the prover could cheat. But we can ask it to reveal the trapdoors immediately after the measurement protocol is over, once they're no longer useful. And well, you might think this doesn't do anything, but we managed to show that firstly, there is an efficient procedure the prover P4 can apply to check that the verifier didn't lie about its trapdoors. And secondly, that this is sufficient for classical simulator zero knowledge. So these are the soundness and the zero knowledge properties that we prove for the protocol I just showed you. Soundness, in particular, we have a constant soundness parameter, not inverse polynomial, and this we inherit from the Mahadev scheme. And for zero knowledge, we have both quantum and classical verifier zero knowledge. So no matter if the if the verifier is quantum or if it is classical, we have zero knowledge in the simulation definition. So that's all I want to say. Thank you.
Questions?
So is the protocol still zero knowledge against quantum malicious verifiers?
Yes. Okay. Yes, it is. Yeah.
Okay. Any other questions? Yes.
Hello. Yeah. Is there an example of an algorithm that we suspect might be in PQP but outside of NP?
So I'm not familiar with particular examples, but one example I think that might be valid is quantum Fourier transform. So it might not be easy to check the outcome classically. Yeah.
Thank you.
Any other questions? Okay, so if not, I think we can thank the speaker again.
Okay.
The last speaker of this session is Claude Crépeau. We'll talk about the RGB no-signaling game.
Hello, everybody. Somehow my talk has been scheduled in the zero knowledge section, but this is not at all about zero knowledge. But since I've been working with zero knowledge for a very long time, I believe I belong here anyway. So the purpose of this talk is mainly pedagogical. This is where I started. I wanted to come up with an example of no signaling, entanglement, and so on that was as simple as possible. So this is my co-author on this work, Xavier Quatreroy from Lugano. We hear things all the time about how entanglement is so strange. Something observed here affects what goes on there. Spooky action at a distance. And the famous Feynman even told us that nobody can understand quantum mechanics. Now, with this kind of attitude, nobody will ever understand quantum mechanics. So, in order to explain quantum mechanics and give examples to people around us, we need simple examples. So, I wanted to find something easy. Now, to do that, I use results that Bell initiated in the 1960s when he gave what's called Bell inequalities. He wanted to give evidence that entanglement does more than classical. And in order to do that, he defined what he called locality. And locality is what you get if you have two people or more, but I'll stick to two people during this talk. Locality is what you get if you allow people to use determinism, so they can compute things locally, and they can share randomness, and everything they can produce like that without exchanging messages is what we call locality. Now, of course, if they can communicate, there's a lot more that they could do. If they can communicate because they exchange messages, the set of things that they can produce this way is much larger. And basically, what entanglement brought is the fact that there's something between locality, what we think is normal according to classical physics, and what we can do with signaling. So entanglement is what people think is the spooky action as a distance, and I'll try to exhibit that it's not, and that you can all go home and explain to your family the kind of things you do. Now, I'm going to explain this in the context of non-local games. Non-local games is a scenario where you have, say, two criminals that are going to be interrogated separately. And so before they get interrogated, they're allowed to exchange randomness. So this is what the dollar signs they're exchanging at the bottom means. And they're going to be interrogated by a policeman, but in a context where they can no longer communicate. So they cannot exchange messages during the interrogation process, but they can use their own local computations, and they can use they will get questions from the policeman, and they must compute their own answer using the shared randomness and give them back to the policeman. Now, this is typically why people get interrogated in police stations separately, because if you interrogate them together, as soon as one of them replies something, the other one is going to agree to it, whether it was true or not. If you separate them, you get a lot more power, and that's exactly what these games do. Now, we're considering two models, the local model as well as the entangled model, and in the entangled model, it's almost the same, but the criminals are allowed to start with quantum states instead of randomness, and they're allowed to apply measurements to their part of the states during the process. So when they're asked something from the policeman, they can pre-agree on a set of measurements they can do, like a camera, something to measure length, something to weight, and something to listen to heartbeat. These are measurements you can apply to a physical system in order to extract information. And you can use those so when the she-like criminal receives a question A, she can apply a corresponding measurement, say the camera, to obtain information X about her state. And when the he-like criminal receives an input B, he can apply a measurement B, which is to weight the state, obtain a Y, and reply that. So by doing this, they can also try to win the game. And if they can use entanglement, it turns out that they can actually do more. Now, I haven't said what winning the game means, but ultimately, winning the game is established by a relation on the A, B's, X, and Y's, and we declare that certain quadruples, A, B, X, and Y, are winning, and the other ones are losing. And we want to establish their success probability, which is the probability with which they can win by selecting a quadruple that is among the winning ones, while the leftmost character only knows A and the rightmost only knows B. Now, all this is presented in terms of strategy. And a strategy for two people is simply any distribution that, given inputs and inputs A's and B's, will select outputs X and Y according to some rules. And we describe all these strategies and we can compare them to each other. Now, the simplest of all the strategies that we can adopt are the deterministic one. So among the strategies, those that are deterministic only involve one character with his own input to compute its own output, and similarly on the other side. So there's no connection between them whatsoever. Now, the next step is that if you allow them shared randomness, then it's almost as weak, but this is what now we call local. So they have local computations that are deterministic and local randomness. Now, this is the simplest model, and this model is very convenient, and we're going to use it a little bit all over the place because I'm going to define a notion of relating strategies among each other by using local calculations. So I'm going to say that the black strategy in the box implies the purple strategy if there's a local strategy for the two criminals where they use local calculations and shared randomness. But on top of that, they're allowed to use black boxes. So if you give them black boxes and you let them use them as much as they want, we say that the black boxes imply the purple box if I can implement the purple box by using local operations and as many instances of the black box that you like. Now, when I say implement, I don't exactly mean absolutely equal, but if asymptotically you can get as close as the purple box as you like by using as many black boxes as you like, then ultimately you get that the black box implies the purple box. So with this in mind, we defined a special box that I call the signaling box, the SIG box. And this box is very obvious. It receives an A on the left, and it outputs A on the right. So this is signaling the value A from left to right. And at the same time, it's signaling the value B from right to left. So this box is just letting them talk to each other as much as they like. Now, I claim that every strategy for two people can be obtained locally using signaling boxes. So if you're allowed to signal on top of being local, then you can do any strategy that you like. You can just talk in the middle of your strategy. So this is a diagram that I'm going to come back to many times. It is what I call the non-locality hierarchy, and it contains the largest class of all these is the sig class of all the strategies that you can obtain through the signaling box. So this is the signaling box, and every thing that follows from it is in the signaling class. Now I'm going to specify two different types of signaling that are very similar. I'm going to call it one the right signaling, where the information coming from the right side goes nowhere, it's lost, whereas the information coming from the left side goes to the right side. So this is signaling, but only in one direction. Now, of course, this is weaker than the previous one, because the previous one could go in both directions, but this one will define fewer strategies. So I use this color to represent the red strategies, the right strategies, and the left strategies are defined similarly from right to left, and then I can obtain all the strategies resulting from this one. So within the set of all the strategies, some of them can be obtained by simply only signaling to the right, some of them only to the left, and some of them can be obtained either way, and some of them require more. And finally, an obvious strategy is the identity. If I give you a value A and you just output A back, and if I give you B and output B back, then you're doing nothing with this box. The box is completely useless. But if you have local operations on top of that, then everything in the local class can be achieved from this particular box. All right, so on top of that, we're considering those obtained by entanglement that I'm going to call entanglement-assisted locality, and something else that's called commuting operators, but let's ignore it for today. Now, the game. So the game I wanted to introduce you came after I read this entry on Quora. Someone asked, could someone explain quantum entanglement like I'm 5-year-old? And this guy, John Hudson, who's a former quantum mechanics student from Stanford, gave this explanation. And I kind of like the explanation, but unfortunately, it's a signaling strategy. What he's describing here can actually be used to communicate. And that's not the point. Yeah, but the idea was good. So I started from what he wrote, and I said, OK, now let's find something really simple that will do exactly that. Now, what do we have in these examples that we explain to people all the time? One of them is the magic square. The magic square is this primitive. If you know it, wonderful. If you don't, go read about it. I mean, the problem with this thing is you have to talk about binary values, a 3-by-3 matrix, and you want that the sum of each row be even, each column is odd, and so on. I mean, that's fine if I talk to computer scientists or even typical science professor. But if you want to talk of these things to your family or, I mean, people with almost no math, there's no way you can explain that to anybody. It's not going to work. The PR box by Popescu-Roerlich is the other example. The XOR of the output is the AND of the inputs. This is great, but what if you don't know what XOR and AND is? You're wasting your time. So, I mean, you can try to make this as simple, but okay, but it's really mod 2, and it doesn't work. Okay, so it just doesn't work. I mean, these examples, they're fine for us, but they're not fine for everybody. So now let me tell you a little courthouse drama. You have policemen, and they say we interrogated these criminals, and I swear they were talking. Now the criminals say, okay, go ahead, just prove it. Okay, I'll prove it, said the policeman, and then they start laughing. So let's see what happened. So this was in the police station. You have 2 interrogation rooms, 2 policemen, 2 criminals. You have the bus, you have the main place, food room. Let's stick to the interrogation rooms for now. Now they played a little game. They asked them questions. What did they ask them? Well, the game is called RGB, as in red, green, blue. The policeman they pick a random color out of the tree, independently, individually. So that policeman picked red and set that to his local criminal. Now the criminal must respond the color which is not the one given. So if he receives red, he must answer green or blue. Okay, up to him how he does that. So the first constraint is that the criminal is not allowed to give the same color back. Same thing in the other interrogation room. The other one picks a color, one out of the three, gives that to his local criminal. He gives a color back, not allowed to be the same color. Now, to make it interesting, because if that's the only condition, it's very easy to win that. Now, to make it interesting, let's say they're not allowed to give the same answer back. Now, this is the game. In order to win the game, the criminals must reply different colors from what they're given, and they're not allowed to give the same answer. That's it. You can explain that even to 5-year-old. Because all you need here is an understanding of what different colors are, or a different anything. So using this only operation difference, this is not the same as that. You have an example, well, I'm going to show you, you have an example where this is actually a no signaling game, which has a quantum strategy better than local. Okay, so this is the general case. You give an A, you get an X back, you give a B, you get a Y back, and the condition is that A should not be X, that shouldn't be Y, and shouldn't be B. And this should work, of course, whatever the distance between the parties. So if you have an interrogation going on Earth, an interrogation going on Mars, they should succeed with proper probability. So this is the game. And the winning condition is what I showed you. Now, there are two ways to win when the two colors given are the same. So if we look at the bottom two rows, if A and B are the same color, then the answers must be the other two colors, either green-blue or blue-green. That's it. These are the only two ways you can win. Now, however, if you're using different colors for A and B, say red and green, then there are actually 3 ways that will allow you to win this game. So these are the 5 ways you can win the game, depending on what your inputs A and B are. So you can make this general whenever the top 3 rows and whenever A and B are different, and the bottom row is whenever A and B are the same. Now let me go through a number of possibilities. What about deterministic? Now, if I want to do deterministic, it means that whenever I get a choice, I must always give the same answer back. So let's say horizontally, if I see blue, I always give red. If I see green, I always give red. If I see red, I always give blue. And so on. Vertically, if I see blue, I say green. If I see green, I say blue. If I say red, I say green again. Now, this strategy doesn't win all the time. It actually wins 8 times out of 9. The dark purple square is the location when they give the same answer back. So this strategy wins 8 times out of 9 if you're acting locally. Now, there are all sorts of strategies. This one wins 4 times out of 9. This one 5 times out of 9. Now, I claim that this 8 out of 9 is the best you can do. That you cannot, using deterministic solutions, do better than 8 out of 9. And I can show you this in one slide, 3 lines. Now, in order for A and X to be distinct, and because A can take all 3 colors, X must take at least 2 of the 3 colors. Because if you take only one color, if X is always the same color, then it's going to be the same as A sometimes, and we disallow that. Now, for the same reason, Y must also take at least 2 colors. Now, if you have X taking at least 2 colors and you have Y taking at least 2 colors, and there are only 3 colors, there must be a location where they are the same. And this proves that whatever you do deterministically, there will always be one of the 9 entries where the 2 colors are the same. So the best we can do deterministically is 8 out of 9. Now, I'm going to consider now a very special solution to the RGB game. I'm going to consider this very exact distribution where I take only 2 of the 3 cases at top and at the bottom. Now, it turns out that this particular strategy is actually equivalent in the way that I mentioned to the PR box. For one direction, if I have the RGB box and I want to use it as a PR box, you just rename your inputs according to colors, you interpret the output as bits, and it's a PR box. So there's a subset of the input outputs that's actually a PR box. Now, in the opposite direction, if you have access to 2 PR boxes, you can actually implement an RGB box. So you can go to the paper to read these details. But basically, if you have 2 such boxes, you can implement the RGB box. Now, what about the courthouse drama? The courthouse drama ends by the judge saying that they're not guilty, because the policemen were trying to convince the judge that the criminals were talking, but indeed, the RGB solution that they can use doesn't allow signaling. And therefore, it's not a proof that they were signaling. Even if they were winning the game 100% of the time, it doesn't imply that they were signaling, and therefore, they're not guilty. Now let me conclude by telling you just a little bit about the quantum strategy. The quantum strategy wins 11/12 of the time. And it's a very simple strategy. You define 3 measurements. The red measurement separates the 0 from the 1 state. The blue measurement, these 2 diagonal states, and the green one this way. And basically, if you start with an EPR pair, you get the measurement described as green, red, or blue. You make the measurement, you get the outcome, and this will succeed 11th out of 12. All right, let me... Now, proving that 11 out of 12 is the maximum, well, that's about half our paper. So you go read the paper. Now, in conclusion, what I presented is a local strategy for this game, the simplest game I could come up with, which is 8-9 success probability. The quantum entangled one is 11/12, and the no signaling one is actually winning with probability 1. Now, this is the picture I showed you initially. No signaling is exactly the intersection in left and right signaling, and that's one of the results that came out of this work. We have that the PR box as well as the RGB box are complete for this class, so anything in the class follows from this particular game. We know that the magic square is in the entangled, but we have no idea if there exists a complete box for entangled, nor commuting operators. So this is my open question. Is there a complete strategy for entanglement? And if so, make it as simple as possible so that everyone can find out about it. And I thank you very much. I just want to use one last minute to tell you, in case you didn't know, that QCrypt is going to be in Montreal in August. And so I encourage you to go check out the web page. Registration is about to open this week. And the very last one is very personal. I have an extra baseball ticket for tomorrow night. So if anyone is a baseball fan, then just come to me. I have an extra ticket. I'll be happy to give it away. All right, thank you.
Questions? So I have one question. So what happens when you have more than 3 colors If you try to define a
Right.
version.
Well, if you go to 4 colors,
Yes.
then it's totally obvious because one of them is going to stick to 2 of them,
Okay,
the other one
okay.
to 2 of them. So if you have 4 colors, it's very easy to win all the time. However, if you go to more people, if you have like 5 people and 6 colors,
Yeah.
I think this generalizes very easily. That if you make more people, more colors, and you request that they cannot be the colors that they're given, and they have to be all different from each other, I think the game generalizes pretty easily to more people. But this is one of my students working on this as a summer project, as a matter
thank
of
you.
fact.
The questions? Yes?
Yeah.
When you had your left channel and right channel, does it make any difference if the people using the channels know what the channel is? So when you get the answer coming back that's actually hasn't come through from the other side, if you know or don't know whether that's happening, does it make any difference?
Well, my first guess is no, but I'd have to think about it a little bit deeper. I mean, we assume that they know the channel. Now, if you don't know what the channel is, I mean, ultimately, if you use the channel many times, it's not clear because it's hard to conclude anything because you cannot exchange information further. So I'll think about it.
Okay, maybe one last question. Anybody? Is it fine? Okay, then thank you again.
All right, thank you.
Before we close for the day, so the poster session will start in about 15 minutes or so you have time to take it a little easy. And there'll be light refreshments as well available throughout the poster session. So yeah, that's the last thing for the day today.